And thank you everyone for joining us today. I see a number of familiar faces in the room. If you've got any questions as we go along, please raise your hand. I'd like this to be as collaborative as we can possibly make it. I should also point out that you have one of your local experts, Jonathan, over there, who has been instrumental in a lot of the technology development that I'll be talking about today. So I've been doing systems and networks since the early 80s. I installed the first Ethernet in the Asia Pacific region and the first fibre optic Ethernet. I've covered everything from DECnet, SNA, X25, OSI, through to extended rooted InfiniBand. That's pretty much been 110 BPS up to 100 gigabits per second. I created and owned a national ISP in Australia, and we had a microwave network which covered Victoria, which is one of our southern states. I was chief engineer for AARNet and ran national and international development. I've been involved in the Australian government ICON network, one of the densest fibre optic networks in the world. In the area of Singapore, we have 188,000 kilometres of dark fibre, which connects all functions of Australian government and the National University. I ran advanced communications research for our national university, and I'm currently working as networks manager at the National Computational Infrastructure, which is our version of NSCC. What we're going to look at today is some of the history of data transfers, the problem space that we're going to be examining, the networks that we have to work with, the capabilities that we need to do big data transfer, some thoughts about instrumentation, the hardware platforms, storage, and then I'll move on to conclude with research platforms. So Professor Lee, who's been involved in this for longer than me, I've got a video of Prof. Lee at an ASEAN meeting talking about 1.5 megabit per second microwave connections and satellite connections which linked our region. We've gone a long way from our early research networks in the region to today's 100 gigabit per second high-speed networks that we all share. Big data now underpins global research collaborations, and transferring these big data sets requires high bandwidth, tuned systems, and also a really good performing storage system. So let's look at where the problem space is. The global research and education network is typically a high bandwidth, high latency network. This differs from the commercial network quite significantly. Most of the commercial networks are focused on providing either a metro, state, or national level network service. As national research and education networks, we connect all of our countries together. One of the issues that we've found, though, is that traditional TCP/IP-based file transfer tools don't scale well into this high bandwidth, high latency environment. And they'll typically perform 1 to 2 orders of magnitude below the available bandwidth, which is really disappointing if we've spent a large amount of money on building advanced high-speed networks that we're not able to fully utilise them. The Science DMZ, which is a concept pioneered by the Energy Science Network in the US, handles the last mile problem of this. Our campus networks today have changed from the way they were 20 years ago. Now, campus networks are seen as a business critical service. So they have firewalls, IDS, security monitoring. We also suffer from campuses being of different ages. So you can't guarantee that even though you're delivering data to the campus edge, that the campus will have the capability in terms of fibre or network within the campus itself to deliver 100 gigabits per second service to a particular lab. So most of the remote data services that we use today, and the most prevalent one being the World Wide Web, is based on a protocol designed in the 90s called HTTP. As I mentioned, the tools are optimized and tested within a regional environment. So if you're developing the next generation transfer tool, of course you're going to test it out in a metro environment here. or you may test it out in a regional environment. What very few tool writers do is test it out in a global network environment where we're able to actually apply real resources, real storage, and have real data sets we need to transfer. So as I mentioned, Europe optimization is good, America's optimization is good, Asia optimization pretty good in most cases, depending on where the tool originated from. But from Oceania, Australia and New Zealand, we suffer from having extended networks. We're on the other side of the planet, we're a long way from anywhere, either by the Pacific or via the west coast of Australia reaching up into Asia. Also, the TCP-based protocols suffer from TCP tuning issues. So the window sizes that the TCP protocol will initially open, which congestion control algorithm is used. So I'd like to just divert that TCP is typically a lossy network. It's designed to handle the underlying network not being reliable. It was built by the US military to provide a reliable and sustainable network in case of nuclear attack. There are a lot of pieces in that network which deal with that unreliability and just rely on the higher level protocol to fix things up behind the scenes. However, our big transfer tools are really sensitive to very small packet losses. Even less than 1% will cause a severe performance degradation. To perform these big global transfers, what we find is that all sites, all network elements across the whole path must be tuned. Now, this becomes a logistical nightmare with running up to 20 network operators, sites across the world and having everyone aligned and trying to get everyone working in a common time zone is almost impossible. So we tend to have weeks of windows of network tuning, backwards and forwards on email, and lots of it. So what we've seen is that our Science DMZ and DTN nodes, they perform pretty well, but they're a small subset of some of the global data that we need to move. And as I said, these techniques don't scale at all well on a global scale. You know, having to have 20 parties involved takes a lot of work. So the commercial response to some of these issues by FANG, Facebook, Amazon, Netflix, and Google, is to put in distributed local content distribution networks. So for example, Netflix will have a server sitting in Singapore with all of their content on it, which is connected into your local ISPs for fast delivery. That way, you don't sit on your television waiting for the spinning wheel while you're buffering. One of the differences in this space is that we're dealing with what's called elephant flows. Now, the majority of our network traffic is what we classify as mice flows. So typically your email, your web browsing, you send a small packet out, you get a flow of data in, you sit and wait, you do the next thing. Even Netflix and video streaming is considered mice flows. So they don't run for weeks or months or years of continuous data flow. They might happen in minutes, perhaps an hour. Whereas elephant flows are long and sustained high bandwidth flows. So typically we try to optimize the network to be efficient for either sort of flows. We've got a lot of expertise in optimizing for mice flows because that's where the majority of our network business is. But these elephant flows are able to cause congestion throughout the network. They require dedicated devices to actually make them work properly. So what's driving this is the requirement for what we call friction-free data movement. Our research scientists don't care at all about any of this. They just want their data where they need it, when they actually get to use their supercomputer allocation. Now, wasting that researcher's allocation waiting for data transfer is really wasteful. So the researcher wants something that's easy to use. They just click a button. It's got to be secure, potentially using a federated access system, so that if you're collaborating, so if someone from NUS is collaborating with someone from ANU, the universities look after that authentication. They make sure that you're still on staff or still a student and that you're able to collaborate. The network and tools need to have the data in the right place at the right time. We don't want the researchers hanging around waiting, wasting their time. On the technology side, we also need to be able to effectively use different tiers of storage, from NVMe, solid-state disks, spinning disks, and tape. Some of these data sets are too large to have sitting on dedicated hard disk resources if they're not being accessed all of the time. One of the things we've been looking towards as we create research platforms is a researcher creating a data intent definition, telling us where the source is, where they'd like the data moved to, their transfer priority, and the sort of storage performance their HPC job is going to need to use to run against that data. What we've also considered is putting in an optional network intersection capability, and I'll get to that when I get to research platforms, but basically saying to the underlying network, it's more efficient to run this transfer in Europe and copy the data back to here for the researcher, rather than running the transfer from Singapore to a source in Europe or the US. So the TCP/IP protocol that has served us well for the last 20 years doesn't perform well under the conditions that I mentioned. So typically, this is the sort of performance you see on a local area network. The further we go in terms of distance and looking at international, the longer the round trip time we have on the network protocol. Any packet loss means that we need to basically tear down all of our congestion management that we've established over a session, and then gradually open the network window back up again until we hit a point of congestion. Now, the network's response to congestion is throwing packets away. So we want to ramp up to where the freeway is running at optimal capacity. We don't want to hit the traffic jam situation, because if we do, we throw all of those cars away and start again. What I'd like to talk about now is some of the existing data transfer patterns we see on some big data movement that we operate around the world. I'll start with the European Copernicus Sentinel system, talk about CMIP 5 and 6 that we're currently doing at the moment, and also talk about some of the results we achieved using InfiniCloud, using both DSync and BGFS. So Copernicus is one of the most exciting satellite missions that we've seen in the last decade. It's 6 pairs or triples of satellites which are doing continuous round-the-clock Earth monitoring. The sort of resolution that we're able to get out of these satellites is absolutely exceptional. Sentinel-1 is a polar orbiting all-weather day and night radar imaging mission for ocean and land. Sentinel-2 is polar orbiting multispectral high-resolution images. Sentinel-3 is a multi-instrument mission to look at sea height, sea surface topography, and land and sea surface temperatures. Look at ocean colour and land colour with very high accuracy and reliability. Sentinel-5 Precursor has been launched now. It's looking at a multitude of trace gases and aerosols within the atmosphere. Sentinel-4 will be earmarked as a replacement for the MetroSat 3rd generation satellite, which is another Earth monitoring satellite primarily focused on Europe. Sentinel 5 will take the work from the Sentinel 5 precursor that's currently running, that's due for launch next year. So the instrumentation package is being just tuned at the moment. Once again, that's a high-resolution atmospheric particulate monitoring system. And Sentinel 6 is another radar altimeter dimension to measure global sea surface height. Some of the things we can do with this data from Sentinel is disaster management. So the Sentinel data will give us less than 1 millimeter deformation on the Earth's surface. One of the data tests that we did was using an artificial intelligence system to detect variations in earthquakes and to actually plot magma flow by looking at the microscopic changes in the ground surface, the ground altitude. We're also using the Sentinel data for marine disaster management. So for those of you who are aware of Australia will know that we have the Great Barrier Reef. We have quite a lot of commercial shipping traffic which flows around the barrier reef as well. So we use the Sentinel data to look for any oil spills, to look for any vessels that are deviating from their designated route, and more particularly for any vessels that have been moored which have broken their moorings. What we want to really avoid happening is having an oil tanker running aground on the Great Barrier Reef. So we track in real time all ship movements around Australia and coming across our borders. What we're also considering using this data for is maintaining our fishing zones and also looking at using it for security to determine if we're seeing people smugglers trying to land people in Australia. So the Sentinel mission is run by the European Space Agency. All of the data from the Sentinel systems is free. So if you'd like to start doing some experimentation on satellite Earth sensing, Sentinel is the place to go.
What's the resolution? Will it be able to give us a map of the temperature map for, say, Sentinel-3, the land temperature of Singapore across a period of 24 hours?
1 kilometre to 10 kilometre.
1 kilometre.
Yeah, this absolutely blows anything we've seen away in terms of commercial satellite systems.
And it's free.
Free.
Who do I talk to?
I'll be getting to that. So the Sentinel data is actually delivered from 2 European sites. One in Frankfurt, connected to DFN, which is the German Research Network, the German version of SingAREN. Which then connects into GIANT, which is the pan-European network, which connects all of the countries in Europe together. This is somewhat equivalent to APAN or TN. The other site is in Athens, connected by the Greek research network, AARNet, which is also connected to GIANT. Now, the bad news. Sentinel is an object-based download system. So they've chosen to use HTTP as the underlying transfer mechanism, which means that all of our really advanced network tools that we've got for high-speed data transfer aren't applicable. So we've pretty much got the typical massive website that we need to mirror, and Australia's right at the other side of the world. What we do is run 15-minute periodic queries to the ESA hubs. We also don't get any indication of what's going to be published. So as the satellites move around, we might not get much data for 20 hours, and then the 2 ground stations will be in sight, and we'll get the whole day's data downloaded and burst to us. For some of our security requirements, we need to get that data pretty much online immediately it's published. So we've got about a 1-hour window that we've got in terms of attempting to catch up with this data. Also, to add more complication to this, each hub has a different number of available download quota slots, so we can't just go, let's fire off 1 million of these things all at the same time. We need to tune it for other people using the hubs, and we need to be fair and share. Republished product sets may also appear without notice. We had an example 2 weeks ago that it was detected that the alignment of one of the sensors on one of the satellites was not exactly right. So they went through and reprocessed and republished a whole year of data, which suddenly appeared in our active queue with a year of data when we had a 1 hour window available for doing backlog downloads. So one of the mechanisms we used to actually work around this was using a very traditional internet application called Squid, which has been around for at least 20, 25 years. By using Squid, basically what we're doing is transferring the download to much closer to the source. Our colleague that some of you will know, Dr. Marek Mikelewicz, was with ACRC and has moved to ICM in Poland and has been very grateful in terms of providing the test bed that we could use to actually see what the difference would be. So a client at NCI requests the download. We've got a Squid proxy running at NCI, which in turn talks to the Squid proxy running at ICM, which transfers the data to a local cache in ICM, and then transfers it back to us in Canberra at NCI. What we observed was a 2 to 3 times improvement in the data transfer performance, just by plugging a caching infrastructure in the center. What we're also looking at is a tiered cache model using AARNet-X, and I'll talk about AARNet-X as we move along. So CMIP 5 and 6, so moving from Europe over to the US, CMIP 5 and 6 are the coupled model intercomparison project. It's basically looking at Earth atmosphere circulation models. The US is the remote site, and in the case of CMIP, NCI acts as one of the regional hubs. I should mention also NCI is one of the regional hubs for Sentinel, so it's also critical that we bring the data and have it on this side of the world for the Asian community to access. CMIP 5 and 6 use also a fairly old file transfer mechanism called Globus Grid FTP. However, this requires a specialised GSI certificate setup, which means we can't just use the standard Globus toolkit as we normally would. Currently, we're running final reconciliation of the CMIP 5 data sets, which is due to finish in the next month or so. And we're currently looking to do a 10 petabyte transfer to keep a copy of the CMIP 6 data that we're interested in. One of the most exciting things we've done in the last decade is a joint project between ACRC, NSCC and NCI called InfiniCortex and InfiniCloud, where we extended InfiniBand, which is typically a data center technology, around the world. We connected ACRC, NSCC, NCI in Australia, TiTech in Japan, Oak Ridge in the US, Georgia Tech in the US, and also the University of Reims, who I forgot to mention here. We've used this as a demonstration technology on the show floor of supercomputing, and I'd like to thank Jonathan for all of his hard work and putting up with a million emails from Australia about, can you just do this for us, please? Thanks, Jonathan. One of the profound things we saw by using extended InfiniBand was that we took what ran over a 10 gigabit network using a traditional rsync protocol of 3 hours of a nearly 300 gig data set, came down from 3 hours to 7 minutes, and a 1.4 terabyte data set, which took 9 hours on traditional TCP, came down to 24 minutes. So it's a pretty profound increase in data transfer speed just by swapping out the underlying TCP protocol. We also did some work with what's called BGFS, which is an open source distributed parallel file system developed by the Fraunhofer Institute in Germany. It's optimized for high performance computing. It supports both TCP/IP and RDMA, which is the InfiniBand network transfer technique. One of the good things is that it also supports a thing called RoCE, which is RDMA over Converged Ethernet. So this lets you run a supercomputing application using an underlying TCP network. InfiniBand provides a POSIX style interface rather than an S3 style object interface where you use HTTP GET and HTTP PUT to manipulate the data. And this was proposed as the DTN interconnect file system for Prof. Tan's data wormhole project. Okay, I'd like to move on to Science DMZs and DTN nodes. So the primary reference site that I would point you to for high-speed data transfer is fasterdata.es.net. ESNet is the US Energy Science Network, which was responsible for connecting up their major high-energy physics facilities. ESNet's provided pretty much the definitive network tuning guide for high-speed data transfers. It has sections on Linux tuning, talks about the Science DMZ, a lot of information on different network tuning, also gives you some idea about what you can really expect to deliver over your network. And as I said, it's typically about a tenth. So it's quite disappointing for us network engineers that provide a 100 gig network and then only can deliver 10 gigs of data per second over it. Faster Data also provides guidance on some data transfer tools. So, as I mentioned earlier, the Science DMZ is basically a concept thought up by ESNet, which bypasses all of the firewalls, security devices, packet shapers, NAT, old network fiber, old network cable, by centralizing all of the data transfer requirement on the campus edge. So the campus edge it's also usually connected straight into the high-speed storage system of the supercomputer facility or a dedicated high-speed storage system. These sort of systems provide what's called data mover or data transfer node capability. Now, let's move down to underlying system architecture. We're all familiar with x86. We've all got Intel processors in most of the devices that we use. One of the issues with Intel processors is that dual CPU systems can perform extremely badly. Now, this is because of a requirement to copy data from a device connected from one CPU across the CPU interconnect to another CPU. The location of devices and the execution of code on a particular CPU is called NUMA. This basically allows you to run the process which is talking to a peripheral connected onto a bus on a particular CPU to be optimized to run on that CPU rather than on the other CPU and require the interconnect of the CPU itself. So this was really a problem kind of before Skylake came along. The interconnect we had was called QPI, and it really suffered badly. What I should also mention is one of the architectural limitations that we're kind of facing at the moment is the PCI 3.0 bus, which is used prevalently throughout systems, only has a capacity of 132 gigabits per second. So it's not feasible to run two 100 gigabit per second devices connected onto the same bus. And we're starting to hit the limits of that bus bandwidth. So this drives why we need to have a dual CPU. Each CPU can have multiple PCI buses attached to it, but there is a limit. So on some of our large HPC systems, we'll have CPUs with two PCI buses attached. The CPU can drive each of those buses at maximum speed. This is also starting to become a problem for the next generation of high-speed storage services. So I'd like to dive into some of the Linux tuning that's required. I'm sorry I'm kind of moving around a bit, but I'm trying to work from the network architecturally on the CPU up through some of the elements of the stack. So what we found is CentOS 6 doesn't perform real well in this environment. We can, by making some fairly radical changes, things like increasing the backlog by 250,000 times, increasing the memory available to the absolute maximum for the TCP stack, changing the window size operations so that instead of starting off with these small TCP windows, waiting for congestion and then building up and up and up, we just start flowing at the maximum rate, which means our networks become stressed immediately, but that drives us to actually engineer properly designed, built networks which can handle those sort of flows. One of the most essential things that we found was the second bottom parameter, which is the congestion control protocol. Now, by default, Linux ships with a congestion control protocol called Reno. It works really well in kind of the local and metro area environments that we typically have to deal with. However, HTCP is designed for much longer range environments and is far less aggressive in terms of pushing the window size down on packet loss. We try to keep all of the buffers full. We try to be more generous in terms of being able to throw a couple of packets away if we do run out of buffers anywhere in the path. Now, we've covered the network, some of the architecture in x86. Let's look at InfiniBand, which is the prevalent interconnect technology that we have on HPC systems. It differs quite significantly from the way TCP works. But what I should mention is the primary vendor of InfiniBand devices, their cards can also work as Ethernet cards. So physically, the hardware is exactly the same. What InfiniBand provides you is an interconnect technology for connecting CPUs and I/O. It offers super high performance. It's non-blocking, high bandwidth, currently up to 200 gigabits per second. But of course, as I mentioned, with PCI 3, you're really only ever going to be able to get 100 gigabits per second out of these cards. It's extremely low latency. So the typical application response across a cluster is less than 1 microsecond end to end. It's got really low CPU utilization. By using a technique called RDMA, which I mentioned earlier, instead of an application talking to the network stack in the kernel, the network stack working on the packet, and finally reaching a piece of hardware which sends it out on the wire, instead with RDMA, the application can say, I'd like a buffer of memory on a remote system. The application then puts the packet in the buffer and triggers a send. From that point on, it's out of the kernel, it's all handled in hardware. So it's much more efficient in terms of not wasting CPU resources, particularly in an HPC environment, that are better spent actually doing scientific computing. As I mentioned, unlike Ethernet, it doesn't require a code traversal through the whole kernel. And it was originally designed for large-scale grids and clouds. It offers increased application performance and offers also a single port solution, just like Ethernet, for networks, storage area networks, and application communication. It uses a different concept of network management called fabrics, which uses a thing called a subnet manager to define the network topology when the network initializes, rather than TCP and Ethernet, which works out of the box and we just kind of work it out as we go along with the whole internet being interconnected. One of the really cool things that Jonathan and a couple of the others here and NCI have done is test extended and rooted InfiniBand. Now, we thought we could try this in the kind of traditional way. This technology is typically used to extend, say, have a storage system in one building and an HPC system in another. We thought, let's see if we can run this at trans-Pacific distances. The extended InfiniBand encapsulates this InfiniBand packets in UDP packets. Now, UDP is the fundamental transmission element of a TCP network. So we're using exactly the same network, exactly the same devices, just changing the way we actually flow packets across it. We used a device from a company called Obsidian Strategics called the Longbow, which provides hardware AES 256 encryption. We connected a circuit between NCI in Australia and ACRC in Singapore, and we used two different paths to do that. We thought we'd stretch this, so we ran it from Singapore to LA and then from LA back down to Canberra, so 2 trips across the Pacific, the worst possible network test that we could ever conceive of. What this generated was one of the largest elephant flows that any of our network operators have ever experienced, which was 10 gigabits per second. And because it's encrypted, it's not just chatting when we've got traffic. It is running full speed all of the time, non-stop, and that was for 21 months. So there are a number of other players in the market. Bay Microsystems, who have a device called the IBEX. It runs at 10 and 40 gig. They've also recently released a 100 gig version, and I'm hoping that there'll be some further testing that we can do using the IBEX systems. I know there are a couple that we have on demonstration at the moment. And also Mellanox, the leader in the InfiniBand market, also has 40 and 100 gig extenders, but they're limited range. They're metro only, so maximum 15 kilometres. So as I said, we took the worst possible example that we could work on because, well, we want to actually solve this as a global problem. Having a network of this length basically replicates any path out of Australia. So this will reach to the far end of Europe, it will reach to any part of America, it will reach pretty much into any part of Asia. So that was 2014. By 2015, we'd laid a cloud architecture called InfiniCloud on top of this, which allowed us to run a globally distributed HPC system with jobs able to be provisioned. And Jonathan, again, was instrumental in a lot of the hard work that went in behind the scenes to make this happen. We also try to set challenges for ourselves. By demonstrating at a major supercomputing conference, supercomputing in the US, it really drives us to come up with something new and exciting because we're competing with everyone else in the world for interesting demos and having new technology that we can encourage people to work on. So by 2016, we'd evolved InfiniCloud. The underlying InfiniCortex infrastructure was fine. We moved to distributed provisioning on a per site level. We'd implemented this BGFS file system. We'd used the Obsidian Bowman product, which our first implementation used a single subnet manager in one place in the world to configure the whole network. What we saw that this caused some instabilities if we started stressing the links. So we put isolated subnet managers at each site. So last year at 2017, we kind of backed off in terms of doing a large-scale demo. But by that time, AARNet-X, AARNet is the Australian Academic Research Network. AARNet provides, I've got another slide on this, but AARNet's carriage service is bundled on a 100 gig bearer, but provides each university with one or more 10 gig services. What we were falling behind in Australia, and thanks to Prof Lee for getting SingAREN's 100 gig network up, that allows us to drive our NREN AARNet to set up an experimental network AARNet-X, which provided 100 gig per second network services directly to NCI. What we worked on this was a single system on each end, basically nothing particularly elaborate, But using the Aspira, which is a commercial data transfer system, running at 100 gig, we were able to transfer 1 petabyte in a week in one direction and about 741 terabytes in the other direction. Now, extrapolating this from some of the numbers that we had obtained from the extended InfiniBand, we're still about 20% of what we could achieve on an InfiniBand network of the same size. However, what we did do was a sustained, and we peaked this out at about 55 gigabits per second on a 100 gigabit per second network, which is pretty reasonable for two systems point to point. Now, the easiest way to get around this is just add more systems. Rather than trying to continue to tune one particular system on either end to have peak performance, it's probably, well, it's certainly far more efficient to put 2 or 4 and have them run at 25 gigabits per second, each able to fully, and by stacking them, fully utilize the network capability. So by this stage, we've moved on to CentOS 7, and the amount of tuning required was significantly less. Basically, we maintained the same extended large window sizes, but one of the things we found made the most difference was turning on fair queuing. Now, what fair queuing does is instead of the normal TCP stack operation, buffering packets until you've got the memory full and then blasting them out on the wire, instead fair queuing paces the packets so that they're nicely paced on the wire. This avoids a lot of the congestion issues that we see with normal TCP. And also, putting on my network engineer hat, is much better for the network. Instead of you throwing me this big bucket of data and then having me worry about how I'm going to deal with it, how many buffers I've got, how much memory I need to have in my routers, and all of the switches and devices. Instead, I'm getting a nice regular flow of packets paced at a particular rate. So let's move on to some of our capabilities and requirements. Regional connection. So connection into each of the 3 primary areas. These are the capabilities and requirements I need in Australia to achieve high-speed data transfer. So I need devices in each of the 3 regions, in Europe, in Asia, and in the US, covering the Americas. I need federated access to those. So how we've achieved this so far is by having a very high level of trust relationship where we've given people root access on other people's devices. Now, this works in a small community where we can all trust each other, we can all look over each other's shoulders and know that we're not going to have a bad actor in there. But it doesn't scale in terms of providing a globalized data transfer system. We also need to provide some of the data capacitor facilities, things like local storage. We need to provide container provisioning so that we can instantiate a toolkit that is known and works at a remote site. And VM provisioning is also really nice. It's so much easier to be able to fire up a virtual machine that can be manipulated or configured in any way rather than having to modify the physical hardware there. And I know from collaborating with Jonathan, we've allowed each other root access on our systems, but it's so much easier if we can go, right, here's a VM, we can share that with other researchers and know for sure that we're not compromising the physical device security of something which is potentially connected to our core storage systems of each of our nations. The regional connectivity is really, really important because TCP doesn't scale well for these regional networks, for these global networks. All of the major data sources for data that we want is currently stored in the USA and Europe. However, there is a growing trend to have data stored in China, and the Chinese are a very big part of our regional community here. So to achieve that good performance, we have to tune everything, but locating those data transfer cache nodes delivers 2 to 3 times the observed performance. So globally, Australia and New Zealand share this unique geographical challenge for big data transfers. We've got high bandwidth, but the longest latency of anyone's networks. We're also large consumers of data in high energy physics, climate, and an increasing amount of genetics. What we haven't had, though, is a data source that anyone else wanted to actually access. So it's all been one-sided. We need you to fix your network for us, rather than, okay, we've got a data source that now we globally need to tune our networks to have it work well in both directions. That growing produces a thing called the Square Kilometre Array, which is going to be the largest radio telescope on the planet, shared across Australia and South Africa. So this really adds a level of urgency because we're starting to come online with SKA this year. Our networks, some of you are very familiar. SingAREN is one of the most advanced networks in the region with 100 gig capability. And more importantly, SLIX, the Singapore Lightwave Exchange. That provides a lot of other countries in the region with a connection point, which really makes Singapore this century's transportation hub in the way that it was for shipping in the last century. We also, the SingAREN 100 gig network also connects to Pacific Wave on the west coast of the US. This provides us an intersection point with AARNet, Australia's academic research network, which we built, as I said, AARNet-X, using a complete software-defined network using white boxes. So one of the goals of this was, can we do it for taking 3 zeros off the price tag? And we've actually proved that we can majorly disrupt the major vendor market. This has now caused the prices of all of the network equipment that we're being offered to drop to about 20% of what they were before we published this information. So it's been a major disruptor. I'd like to just quickly show you some of the depth of the global research and education network. As you can see, Singapore is one of the major intersection points for this region. The west coast of the US is also one of the other major intersection points. And there's a 100 gig SingAREN network running. AARNet has their 100 gig network running, and we have AARNet-X. There are 2 network paths out of Australia, a northern and a southern path. We've dedicated the northern path to AARNet-X operation. There is also a smaller 2.5 gig network running from the west coast of Australia over an old fibre system called CME-3. Unfortunately, even though this gives us a really nice fast path between us, this fibre system is down 3 to 6 months of the year on pretty regularly. There's a new fibre system that's being constructed called Indigo, which will connect from Sydney round to Adelaide to Perth and then up to Singapore. That runs over a much better route, which is not dredged up by boat anchors on a regular basis. That will also provide us multiple 100 gig capability. Singapore is pretty much the centre of Asian networking. There is another hub up in Hong Kong, but Singapore is seen as a far safer place to put this infrastructure and also do these interconnects. The fact that you're a sovereign country and are not influenced directly by China is something that is really underlying why you're so well regarded. And Australia, we're typically the size of Europe. We cover from the top of Moscow down to the bottom part of Spain. We've got a 100 gig national network which provides 10 gig bearers. This gives us the flexibility, though, to be able to do point-to-point circuits within the network between any of the 38 Australian universities. And I'd just like to zoom in a little on the NCI network. Our facility is spread over 2 data centres on campus, about 500 metres apart. We have multiple AARNet connections coming in, 5 AARNet 4, 10 gig services. We've also got our Geoscience Australia, which is our government geological Agency, and the Bureau of Meteorology, which is our weather forecasting agency. The AARNet-X network connects into our main primary data centre. We have a number of clouds, and we're actually physically on the Australian National University campus, so we have two 10 gig connections into the campus network itself. So AARNet-X was a new concept that we came up with, which was a completely new paradigm in network design. What we wanted to check out was white box open compute platform switching. Has it reached the maturity level where we can throw away expensive vendors like Juniper and Cisco? Can we replace the proprietary routers and switches and the infrastructure with a much cheaper way to do it? And even more, one of the things that vendors are really expensive with all of us is the price of optics. So we wanted to drive the price of optics down to about 10% by using third-party optics, and we've got 3 optical suppliers who all compete to drive this to the bottom, much to the horror of our Cisco and Juniper reps. So the AARNet-X design used Mellanox 16-port 100 gig switches. These are typically just used as layer 2 devices as they're sold, but they have an x86 CPU, and there are 2 100 gig chipsets out there, the Spectrum chipset from Mellanox and the Trident chipset from Broadcom. Mellanox is the only vendor who has Spectrum, everyone else has Trident. The main differences are just in the difference in blocking and port capability. So we're very close to Mellanox, and so they basically provided all of this equipment for us to build this network on almost for free. The network operating system that we chose was a thing called Cumulus Linux. For those of you who've been around doing networking for the last 20 or so years, networks always used to run on a system rather than a dedicated box. So we've just taken all of the techniques that we learned in terms of running networks on devices and put it into Cumulus. This gives us a 200 gigabit per second national core carried over the optical transport network of AARNet. We provide layer 2 and 3 transport, IPv4 and IPv6, and most significantly, it brings a very low cost for connecting 100 gig devices into the network itself. So let me move on to Science DMZs. Our current design is to connect to our 2 AARNet POPs. We have an NCI Edge. There we have an SN2100, which is acting as a router. We feed 2 100 gig services down to an SN2100, which is acting as a switch, and that gives us 1400 gig ports available for interconnected devices. Connected to that, we have our new DTNs. Now, I'll get on to data transfer nodes in just a minute. The data transfer node is a dual-core Skylake system equipped with solid-state disks and spinning disks. It also has 200 gig interconnects into our core storage system and 2 10 gig interconnects into our existing data center network. We're just at the stage of moving from 10 gig in our data center to 100 gig, which is what led a lot of this experimentation. Some of the supporting services we use, it's provisioned, it's all software defined, it's provisioned using Ansible. We use Libra NMS as the underlying network management system for recording using SNMP. We use Grafana and Telegraph services, Grafana and Telegraph, which is a really great open source monitoring toolkit. And the ONI services are used for device booting and device configuration. Libra NMS for SNMP, the hardware sensors, system performance, looking at interface statistics and alerting when we're having problems on the network. And for time series analysis, InnoDB, Grafana, Telegraph agent installed on all devices, and the Telegraph dashboard. Telegraph is typically our primary monitoring interface. That's the one I have on my screen all the time just to see what's going on our network. It's all x86 architecture. We've tried a variety of NICs from different vendors. The I/O subsystem is something that we really need to look at. There needs to be a a range of different storage tiers in there. We've seen NVMe can typically handle between 10 and 15 gigabits per second. So none of the storage directly connected to the system is fast enough to actually stage the data. However, we've got the 200 gig EDR connections into our storage pool. So we do have the capability to take line rate 100 gig data coming off the network and get it onto disk at line rate. The storage pool will run at 144 gigabits per second. So we've got a little bit of overhead left on that.
Any of the storage is parallel file systems?
It's all Lustre. Yeah. We are experimenting on BGFS, but I'll talk to you about that later. So we've got 2 DTN platforms currently in production. Our 10 gig DTN platform is Sandy Bridge. It uses Mellanox Connect X3, which are 2 generations behind. We've kind of kept with the same underlying storage configuration of 2 terabytes of SSD or NVMe and about 30 terabytes of 1500 RPM SATA RAID 5. Sorry, SAS RAID 5. Our current DTN platform that we're working on is using a Dell PowerEdge R720. We've gone with big vendors mainly because we want the support that they provide. Jonathan and his team have had a great deal of really good work with Supermicro, but the hardware from them we've found delivered to Australia hasn't been as reliable or as stable as the vendor hardware. We also want 4-hour response. So these are mission critical services. They're not just some research platform, research activity sitting on the side. So our storage is Lustre file systems. Lustre is a parallel distributed file system. We also have mass data, which is NFS mounted. That gives access to our MDSS-based tape library. And we've got the tiered storage managing burst flows, and also primarily the hard disk is there so we can continue to do data downloads while the storage is down. This gives us some flexibility in terms of not having to shut down everything in the facility on our quarterly scheduled maintenance. We can continue to do data movement. So just a final thing on Linux tuning. Number affinity is the thing which matters the most, followed by buffer sizes and the congestion control algorithms. Start with CentOS 7. Don't try to work CentOS 6. It's a point of diminishing returns. And fair queuing or packet pacing, which is implemented in CentOS 7, really has a major performance impact. So it's pretty easy to turn on. Okay, we're starting to run out of time. In fact, I've gone a little bit long, but let's talk about, to conclude, some of our research platforms. ESNet hasn't stood still with their development. Instead, there's been a connection of Science DMZs within the US over high-speed networks. That's called the Pacific Research Platform. There's been an initiative to build that network of Science DMZs to look at how we optimize file transfer tools in that environment. In our region, we've recently set up what's called the Asia Pacific Research Platform, which consists of KISTI in Korea, NCI in Australia, Malaysia, NSCC, NUS and NSCC, NSCC in China, and CSIRO, the Commonwealth Scientific Industrial Organisation, which is Australia's version of A*STAR. And we've also got University of Putra Mahart in Malaysia. So the proposed high-level architecture that we've come up with for the Asia Pacific Research Platform extends the DTN concept to have DTNs located at the edge of the TN network in London, which provides us an intersection with Giant for European data transfers, in Singapore for the rich connectivity that SLIX provides, and also for connectivity into NSCC, traversing the SingAREN 100 gig network currently for Singapore data transfers from the US, and supplemented with Indigo when it comes online at 100 gig, the AARNet Southern Cross Transport Network, and Rian's Hawaii Network, which is in the process of being built and scheduled to come online later this year. This will give us both a production and a global test bed that is far larger than any of the other research platforms is looking at. We have full global distribution and coverage with this. Something I'd like to show you is sort of the data flow patterns that we see from Sentinel. It typically floats around 0.5 to 1 gigabyte per second. So it's not a big data flow, it's just a continuous and never-ending data flow. There are a number of data transfer tools that are available which are documented on the ESNet site, and I don't have enough time to go into them. But something if you'd like to look at that has shown a great deal of promise is MDTM FTP. It's a file transfer utility developed by Starlight University of Chicago, which is aware of the NUMA affinity. So it can run the network task on the CPU with a network attached. It can run the storage task on the CPU with the storage attached. It's much more efficient in terms of being able to fully utilize our networks. And just to finish off, I'd like to talk about the Extreme Data Cloud, which we're hoping to use as the underlying infrastructure and orchestration system for Asia Pacific Research Platform. Extreme Data Cloud is a European initiative which ties together a number of existing open source packages and provides a federated authentication system. It's both a software development and integration project. The plan is to be scalable with federated storage resources, basically dealing with some of the concerns that we had in terms of the limited trust network that we have. And the targeted platforms of the current next generation e-infrastructures deployed in Europe. So the European Open Science Cloud, data from CERN, and a number of other ESA, a number of other big data services. It consists of a number of components, Rusio, Indigo Infrastructure, FTS3, EOS, and Raven. They cover storage, federation, and orchestration. So the intent is to have an intelligent and automated dataset distribution mechanism, winding back to one of my original slides where the researcher creates a data transfer intent. That lets us optimize it on the back end without having to involve the researcher on all this tedious network stuff that they don't want to know about. It gives us a policy-driven framework for data management. It allows us to describe the quality of service policies that we want for that data, where it goes onto disk, tape, SSD, and it also provides a software lifecycle management system so that we can all ensure that we've all got the same versions of the tools. Now, this is one of the other issues that we have. Someone will make an advancement and suddenly they're not quite compatible with everything else. Now, when this is production, that's a real showstopper. So you really want that compatibility. It also supports data pre-processing during ingestion. The data management is based on access patterns. So if a researcher in Australia needs to access a data set in Europe, we don't copy all of it if they're only going to access a few gigabytes. We just move that part when they need it. It supports a smart caching system, which we've proved that makes a significant improvement in performance transfers. It handles metadata management. So how do we track all of these big collections that we've got? And it also supports sensitive data handling. Now, this is an area that is really, really critical moving forward. If we're going to look at moving people's genetic sequences around on research and education networks, we really need to have security absolutely implicitly built into this. Yeah, if someone's life or the core of their identity is stealable, then we haven't done our job properly. So typically the typical workflow is the data will be stored on a fast device first. It'll be replicated to multiple secondary storage devices, including tape, potentially at multiple sites. The user can restore their data from any site. So this caters for, say, a catastrophic natural disaster, which actually takes out a supercomputer facility. And as I mentioned, the data management is based on access control. This also provides something really cool that we have to work on as a community, which is how we take the output of scientific research, which has a window of confidentiality while someone's paper is published. But for reproducibility, we need to have that data published automatically to line up with the publication of the paper. In some cases, that's not applicable when it's very private research data or national security data. But for the majority of our data that our users publish, we just want to be able to specify, okay, 6 months or 12 months' time, open the gate, and people can look at it. So it supports a smart caching algorithm, a storage federator to basically provide an underlying authentication and authorization mechanism across multiple facilities, and the capability for HPC centres to allocate, to define how much resource they're going to share and under what sort of conditions with an access policy. The storage is organised into different zones. These can be national, regional or global. What we're trying to get to is a unified data access platform at the platform as a service level, so we can reach exascale computing in the next couple of years. Encryption services and secure storage are needed, and sensitive data management, key storage is handled with OneData. OneData also supports a number of underlying storage layers, POSIX file systems, Ceph, S3. So yeah, there are quite a variety. It's not locked into one particular technology. So the high-level architecture has a user who has access to file transfer services. Everything below this line is mediated by the network, as it should be. The user just tells us what they want to do, and we take care of it, well, the network and the tools take care of it for them. So in conclusion, Science DMZs are basically the gateway to our campus networks, which exist right on the edge. I've gone into a little bit on data transfer node hardware, but I could spend a whole day on the nuances of that. We've looked very superficially at some of the data transfer toolkits that we use on this. We're looking to build out the Asia-Pacific Research Platform infrastructure in Singapore, London and LA during this year. We're investigating the European Extreme Data Cloud components, and we're going to integrate with the existing federations. So thank you very much for your time, and I'd like to open it up to questions if there's any.
Okay, thank you, Andrew. I know NUS have been trying out some DTN nodes. Any questions for Andrew from the floor?
What I didn't put up was my email address, but if you contact Finlay, I'm sure she'd be happy to forward any messages you've got. And just a quick shout out, your local folks at ACRC and NSCC are your primary contact point, and we welcome any collaboration or cooperation you'd like to provide to this initiative.
Yeah. This is Jim from US Information Technology. So for in one of your slides about the demonstration the SC17, you mentioned by use this Aspera 100G data transfer. It can achieve sustainable flow rate is about 55 per second.
Yeah.
So this is for the data transfer or the memory management.
So we peaked 55 gigabits per second, point to point, memory to memory. Yeah. I wasn't in the position to connect this up to our core storage, which had greater than 100 gigabits per second bandwidth. But we're planning that's kind of in our thinking for supercomputing 17 is to do disk-to-disk transfers rather than memory to memory.
So this Aspera is a commercial software.
Yeah.
Is that 23 or 3 terabytes?
Sorry, which one?
1 month, is it?
1 month, 2.3 petabytes per month.
So it's 23 terabytes.
Ah, yes, sorry, out by 1. That's what I get for writing presentations on planes.
So does Aspera work better than InfiniBand desync?
No, significantly lower. InfiniBand desync is the cream of the crop that we've seen in terms of transfer systems.
Are you still saying that desync InfiniBand data transfer is still the gold standard to aim for?
Personally, yeah.
To aspire to.
Yep. I don't think anyone's achieved the sort of data rates we achieved with desync.
Japanese guy, right?
He did it. The one the Japanese guy did was to have a large number of TCP streams running across the different 100 gig. We have 100 gig that's from Japan coming to Singapore to US, and they also have 2 100 gigs that's going from Japan to US. So which they got about 230 gigabits per second. Yeah. But it's using TCP, huge number of streams. Yeah.
So in terms of the percentage of data flow utilizing the line speed, InfiniBand is still able to max out at something like 90%.
98.9.
98. Wow. And whereas this guy is coming up at 55 Gbps over.
Realistically, 20%.
Only 20%.
20%, but 55 out of 100 gig.
That's memory to memory. It's,
okay.
It's not real.
Okay.
Which is why we look at having 4 DTNs in there so we can saturate.
Only 20%. In other words, you're saying that if I need to transfer a steady flow of data across a long distance, continental distance, I would have to pay for 5 times the bandwidth.
No, you have to buy 5 times the number of endpoint systems.
Yeah.
The bandwidth.
Using Aspera.
Just to mention, we've discontinued using Aspera just because of the cost. So we've been looking at alternative file transfer tools. MDTM FTP seems to be the best. As properly said, the other way around this is large numbers of TCP streams. So MDTM FTP is open source. It has the NUMA affinity. It has multiple TCP stream capability, but I don't have any real numbers from what we've seen off that yet. We've just kind of started experimenting on that as a replacement for Aspera.
So how fast, what's the percentage utilization of bandwidth that you think this guy can go up to?
I'd say 25-30%. So the typical 4-to-1 ratio of DTNs to, so yeah, about a quarter of the network performance per endpoint device.
So are you still saying that InfiniBand should be?
It would be nice, but I think you and us are the only ones who have that InfiniBand kind of knowledge and capability to move forward on it. So it was a great experiment, but yeah, perhaps we should take this offline. But I think the vendor space has moved on since we did those experiments.
Okay.
Yeah, I think it's very interesting to know that you're also in your test, you also see that this system configuration in the ETC, the system config, all those changes may affect the performance. Especially in our project test, we also noticed that have to tune in some of those parameters, buffer size, in order to achieve different kind of results.
Yeah, and the
latency may also affect. So we also found that for the shorter latency, we have to use this set of configuration. If your distance is longer, higher latency, then you have to use another set of parameters.
Yeah. So the ones I've given you there are the maximum that everything can be wound up to for the longest distance that we can achieve. But you're exactly right. There's no, here's the, just plug this in and you magically get data transfer nodes. There does need to be tuning, and the faster data ESNet guide gives you kind of, local regional, global, local, regional. What they don't have a lot on is global, and I'm working with Eli Dart, who's the guy who wrote that guide, to add this additional 100 gig tuning in.
Maybe we can learn from your
We're also happy to share our findings, and there's heaps more that I haven't put in here on our experimentation.
Thank you.
Certainly the round trip from Australia to US and back to here is about
383 milliseconds.
Yeah, that's really, really long.
Yep.
In Singapore, we only less than 10 milliseconds.
This is the microsecond. I think it's less than 300 microseconds.
Less than 300 microseconds.
Yeah.
Oh,
From
okay.
US to NTU back to AS.
You mean running through the slick backbone?
Yes, 43 kilometers.
Okay. So how much throughput can you get in your experiment?
We did a file transfer. We can finish about 85 gigabytes data transfer in 9 seconds.
That's pretty much consistent. So about 10 gigabits per second on a 100 gigabit network.
It's about 70 over gigabytes per second.
Cool.
Cool. Yeah. I think just to share with you, we are actually deploying and working with GIS from UK. They are deploying a DTN node on that side, and likewise we are deploying one in SingAREN, but at 10 gig, not 100 gig. I'll note we're not running at 100 gig, but we are planning to deploy multiples of it so that we can support it. But currently we are helping LKC, Lincoln Chang's medical school, in transferring large data, genomics data, to and from Imperial College London. I also like to share with you today is that China is now pairing with us with 100 gig directly. We advertise to them. Huh? CERNet.
Oh, commercial.
CERNet. So CERNet, the Chinese NREN, is paired with us. But that doesn't mean they advertise all their universities there. I hope they do. Then we can reach them quite easily. And we plan to actually test it with them.
Yeah, it's through Hong Kong, or?
Yes, it's through Hong Kong, but we do a VLAN from CERNet internal all the way out to us. So they're 100 gig, hit it, and then we so-called create a VLAN through the Japanese router all the way out to SingAREN router, and then peer with us directly. So we have a little bit more control with it. So it's only one hop away from us.
Right. So when does the Great Firewall of China hit?
Last time when we tested it, it was getting from Hong Kong into CERNet, China. That's where, because it doesn't from Hong Kong, it goes right up to Beijing. CERNet one is Beijing, you see, and we were hit by the firewall. So now with 100 gig, we haven't tested it yet, so to see how much we can push through the firewall.
So the Great Firewall of China is actually TCP/IP based, or it hits you at the VLAN?
It hits us at the IP level. We were going through at the IP level. So I'm not creating a VLAN into that. Yeah. So we're hitting at the IP level. I suspect in the VLAN but I'm not sure.
That theoretically should bypass it.
Yeah, should bypass it, but you never know what they have put in place down there.
Right. The reason is because there are multiple parties in China that want to set up the CDN outside of China, obviously. And so they need a tunnel somewhere through that is not TCP.
Yeah.
And it could also be a data center connection.
That's right.
Because a Chinese data center inside China's firewall do not provide good service to outside, anything outside of China. Now needs to provide a service, a clone or push the data through a CDN method into an external location on the basis that it's a data center to data center extension out of China, residing outside of China.
So we're testing out this VLAN truth first so that they are appearing as if directly with us through that VLAN. We haven't really tried out because we just got notice of it today. So we're slowly learning about it. Okay.
So there are at least 2 projects that can do this.
I think one is Wuxi.
And the other one is now SenseTime.
Okay. Oh yes. Yeah. The other thing is
the capability will be a tremendous boost for them. As we will also get the effect of the flow-through effect of the very key for Chinese services up for external consumption.
we have to try that out and see what can be done through that 100G link.
So how is Alibaba going to work with NTU?
I don't know. I don't know.
Data center in NTU?
I am not sure. I'm not sure whether they are setting up data center or not. It's still the early days, Alibaba.
So going back to the API, we're going to have a discussion with ISC. Are you part of that discussion, right? I see Sean Smith copied the message. So the net effect is struck, and we have Australia, New Zealand, and Singapore initiate the actual technical deployment of a prototypic DTN infrastructure that underlies the first phase of the Asia Pacific Research Platform.
And we'd like to run the Sentinel Copernicus data transfers over the top of it as something mission critical.
Sorry,
We'd like to run the Sentinel data transfer over it as a mission critical, replacing the research activity we've run with ICM. We believe that this should be a sovereign device which is owned by a couple of us for our own national interests. So if it's a, we need to kind of talk the funding, but NCI are remarkably keen to have a remote service in London.
So you actually have a lot of people in Australia working with the Europeans on the Sentinel Copernicus project, right?
Yep.
Are there any out in Southeast Asia?
Not that we've observed yet, but we pick up for political reasons the data to the southern edge of China's borders. But the data is publicly available with the regional hub, and anyone who, I'd like, if you could spread the word that data is there, because there's just, the Europeans are projecting this is going to be a $30 billion a year industry in terms of space observation and subsidiary industries.
So how do you know whether Singapore, for example, and surrounding areas are covered by these satellites? There's something on the website.
Because I set up the bounding box which cut off at the bottom of the Chinese border.
So he can see it.
Yeah. So one of the things that I've thought that this would be really great for is when the burnings happened in Indonesia and suddenly your air quality just falls through the floor. It's not going to have immediate data access, but at least you can look at 24-hour, 12-hour kind of progressions of the atmospheric particulate levels that this thing's measuring. So it could have direct benefit to someone's life here, and if you know a good data scientist, a climatologist who's interested in this, we're happy to make it available.
Yeah. We have a Center for Remote Sensing called CRISP. They use some other satellite information, but why are they not part of this?
This has only been running for the last year or so, and they're still launching the satellites.
Okay.
So we're still at very early days, but the resolution is just so much better, and the frequency of the visits is so much better.
And you said it covers south of Chinese border?
The service covers the whole world. We just only store from the Chinese border down. It's China's remit to do north of that for their regional hub.
So you have data of Singapore, actually?
Yes. And we would, as I said, we don't have much data that people want to access. from our side out. So this is hopefully one of the excellent data collections that we're going to be able to offer back into the region, rather than just being a consumer. We're going to be a producer for this as well.
So are you saying that you're moving data through Singapore to Australia, are curating it, and then sending a fraction of the data of Singapore interest back to Singapore?
Yep.
Okay.
And network flows are typically very one-directional. It's all coming in. So we've been looking, trying to find new data products that actually stress the network in both directions, which also drives some of the funding requirements.
Australia also stores a lot of genomic data.
Yes, and I need to talk to you about this. The tsunami of this that we projected 3 years ago is just starting to happen.
Okay.
Do you have any user-friendly RDMA-based file transfer tools to recommend?
The only one that we had was a thing called Desync from Obsidian, which was a proprietary application that they developed. Unfortunately, Obsidian have entered bankruptcy. So while we have that code still, I don't think it would be ethical if we used it over somebody else's devices. If you have some enterprising students, we're always looking for new contribution into this, and we're happy to provide resources and assistance.
And I'm happy to fund this.
So you've got it. If you've got a good student or a couple of students who are interested in this and want a career in HPC data movement, this is the perfect entree.
How many RDMA type applications have you encountered so far, other than just pure file transfer?
That's out of my area of expertise. I've went off being on the HPC side of things and the application level to data transfer over the last 2 years.
I guess for RDMA to really take off, there has to be a killer application.
We were hoping BGFS would be that killer application, but basically there's just not enough hours in the day for running production and research at the moment. So we've slowed down a lot on where we would hope to have been by now.
So do you see some kind of application running this kind of lossless, jitter-free? You didn't mention and the kernel bypass, zero copy, over deterministic networks like the VLANs that you pull out of China, for instance.
It would be really nice. I just don't think we've got the exact tools yet, but no reason why not. And there are other alternatives to TCP/IP protocol. So if we're dealing at a VLAN level, we can just do UDP and have much more granularity in the flow controls. And that was the initial InfiniCortex. This is one of the things we wanted to check. Are the network devices actually capable of running at these speeds, or what is the limitation? And the limitation is a 30-year-old protocol that we all are relying on.
Keeps coming back to TCP/IP. That's important.
So also, if you've got brilliant students who want to look at the next generation of networking protocols, we can also provide a global test bed and probably more funding grants than they could ever imagine.
So there is a Uzin Society, I can't pronounce the name properly, POUZIN Society, is coming up with a new generation protocol. Have you heard about these guys?
I haven't. I've been focusing on how we can optimize IPv6.
Right, so they are actually re-looking at TCP/IP as the protocol of the global information infrastructure, and asking hard questions like the ones that you encountered and have to a certain extent overcome. And they're re-looking at what kind of protocols and specifications would meet future needs of recently digitalized world.
Excellent. Oh, if we can take some advantage of their work, we should certainly do it. Yeah, one of the things that I kind of need to stress is all of this technology, it comes and goes. So TCP is a means to an end. If there's something better that comes along, we always need to be open-minded and have a look and see if it'll do, solve these problems in a better sort of way.
Okay, I'll stop Timmy from talking anymore. And let's put our hands together. Thanks, Andrew.